Okay, number 4, you need the radius or the diameter to find the area of the circle. So we need to know how long that line right there is, because that would be the radius. So I'm going to focus on just this little triangle with the 8 and what would be the radius. And hopefully remember from regular polygons that if you only have one side, you just need to find the angle. So then you can use trig or special right triangles. So the angle there, the central angle in a triangle, is 120 degrees because it's 360 all the way around and we're splitting it into 3 equal parts. Then when you take the right triangle half of the big triangle, you get a 60. So we have a 30, 60, 90 right triangle. Now you could use trig or you could use specials. Preference?
Right.
Trig. Okay, we're just trying to find the R. So if I use the 60 and the 8 and the R, that is going to be cosine because the 8 is adjacent and the R is the hypotenuse. So cosine of the angle equals adjacent over hypotenuse. Cosine of 60 equals 8 over R. This is where we always mess up because we just multiply both sides by 8 and call it done. You need to multiply by the denominator or it doesn't cancel. Okay, those R's cancel and you're left with 8. R times cosine 60. Can't really do anything there. So now we have to take another one and divide by cosine 60 to get R by itself. Is that my computer making the noise? Or is it something else? Is the what roll? No, I hear like a tone. I'm just going crazy. It's just me. Okay, what am I doing? 8 divided by... I still hear it. 16. R is 16. That means my circumference is 32 pi, and my area is 256 pi. Dayton. Yep, 16 squared. Okay. Any other questions on any of the 4 sheets? Lily?
Number 1.
On this same section? Which is on a different file. This one. Say what?
Yeah.
There. Okay. So you're trying to find just the shaded area here. So to do that, you're going to find the area of the square. And you're going to subtract the area of the circle. Let's see. Area of the circle is actually fairly easy. We already know the radius. So it's going to be pi times 2.1. Is it 21 or 2.1? 21 squared. So that'll be the area there. Area of the square is not a whole lot harder if you do this. That line's also going to be 21 units. So then how long is it all the way across? 42. The side of the square is the same as the diameter. So the area of our square is going to be 42 times 42. So that's 1764. And then 21 squared times pi, 1385.4. I really don't like these calculators. Minus 1385.4. I got 378.6. Okay. Any others? Kelsey.
The second one in that section.
That one? Okay. Weird that you can't see the top. All right, so here we have a rectangle instead of a square. So, and it's inside instead of outside. We need a radius. The radius is going to be like that to one of those four corners. So if I go the other way also, I have a diameter. And that's what we're going to have to focus on. We're going to have to find that diameter, which is the same as the hypotenuse of this right triangle. Okay. So we're going to do Pythagorean theorem. Short plus medium equals long. A squared plus B squared equals C squared. All right, 24 squared is 576. 32 squared is 1024. And that equals 1600. Square root that, and you get 40, I think. Yes, 40. So the diameter of our circle is 40. Means the radius is 20. So area of the whole circle minus area of the rectangle is the method. So pi times 20 squared, pi r squared, minus 32 times 24. Squared times pi. Minus 32 times 24. I got 488.6. Square meters. All right, any other questions on this assignment? Say again, Earl? On this same section? Okay. That one? All righty. This time we have a triangle inside. We need a diameter. We need this side. And we can find that because it was a right triangle. So one side is 3, one side is 4, and one side is unknown. So we're going to do 3 squared plus 4 squared equals x squared. Small, medium, large. 9 plus 16 is 25. So x is 5. Now be careful, that's the diameter and not the radius. The radius is actually 2.5 because it's half of 5. So then we'll do area of circle minus area of triangle. Pi r squared for the circle. 1/2 base, nope, wrong number. 1/2 base times height for the triangle. 3 and 4 are the base and the height because they are perpendicular. Sorry, guys. That's better. So 2.5 squared times pi is 19.6 minus 1/2 times 3 times 4. Your answer is about 13.6 inches squared. Okay. Yeah, we can do number 4. Okay, circle the side of a square. So we're going to do area of circle minus area of square. It's always the big one minus the small one. Here, the square is the easier one because we know the side length. So it's 10 times 10. And the circle is the hard one because we don't know the diameter or the radius. But if you pull it out like this, you have your right triangle. It's 10 here, it's 10 here, and you can find the hypotenuse. So you can do Pythagorean theorem, or this is a 45, 45, 90 right triangle. So I know my hypotenuse is going to be 10 root 2. But if you do Pythagorean theorem, you're fine. You'll just get a decimal. That is the whole diameter. So my radius is going to be half of that, which is 5 root 2. Okay. So for my circle, I'm going to do r squared times pi. Actually, I'll square it right here. 5 root 2 squared. 5 root 2 times 5 root 2. That's 25 times 2. It's going to be 50. 5 root 2 squared is 50. So the area of my circle is 50 pi. We're going to do 50 pi minus 100 for the box. And you get 57.1. Now, if you used Pythagorean theorem and you didn't get exactly 50, you got like 49.8 or 51.2, that's fine. It's close enough. Okay. Any others on that assignment? Okay. Go ahead and open up your notes for today, which are on tangents. Now, you learned a little bit about tangents by force yesterday because you either looked it up or you asked me. A tangent line is just a line that meets the circle at one specific point. So this is called the tangent line. And then the point where it meets is the point of tangent C. One single point. All right, tangent lines have some special relationships with other things going on in the circle. First of all, If a line is tangent, then it is perpendicular to the radius that meets at that same point. So if the radius meets at the point of tangency, then that forms a 90-degree angle. Okay. The radius meets at the point of tangency, then it forms a 90-degree angle. Okay, so using that information, we have SE as a radius, ET is a tangent line. So they've already marked that that angle E is a right angle. Is the radius and the tangent are both meeting at E. If SE is 12 centimeters and ET is 16 centimeters, how far is T from S? So the question is, how long is segment ST? How do we find it? Pythagorean theorem. Where does the 12 go?
A.
Where does the 16 go? Good. Because the C, the side that we don't know, is the long side. The 12 squared is 144. 16 squared is 256. Add those together, you get 400. So C is 20. Centimeters. Okay. All right. This problem, like the story behind it doesn't really make sense. But we've got these two tangent lines that are coming from the same point. So O is the point of tangency for the top line. W is the point of tangency for the bottom line. The question is, what is the radius of the garden? How do we find it? Billy? Pythagorean theorem again. This time, where does the X go? Go ahead, Eddie. It goes to the A. Equals 25 squared. 25 is the largest side, so it is our C. If you square those and then subtract them, you get 49. So X is 7. So our radius equals 7. All right. What else do you notice about these two triangles? Why are they congruent? Yeah, it's not enough to make it congruent, though. Ethan?
Isn't it side to side angle?
It is one of those, but not side-side angle. Now, remember, we don't like that one. But which one is it? What's congruent here? 25. Congruent to itself, yep. The 90-degree angle. So we've got both of those. So we've got an angle, we've got a side. You sure? What do we know for a fact? We know that that was 7, and TW also has to be 7 because it's radius of a circle. So those are our three things. We've got a side, and we've got an angle, but it's not ASS. It's actually hypotenuse leg. That's the one, when you get ASS, you look for hypotenuse leg because it's right angle. So they are congruent. You could see them, but you just couldn't tell me why. So if I have 24 at the top, that means I've got 24 on the bottom. And then what's happening to this angle E over here? It's shared, and it's shared equally because they're congruent. So those are bisected, or the two pieces are the same. And angle T, the same thing's happening there. Those two angles are going to be the same. Because we've got congruent triangles, so we've got 6 congruent parts. Okay, and that leads us right into the next theorem. If 2 tangent segments are drawn from an external point, so if there's one point and they're both meet it, then that is going to happen every time. Those 2 tangents are going to be congruent because they are being formed by 2 congruent triangles. So anytime 2 tangents meet outside the circle at a point, you can kind of think of that as like a hanging basket. You got 2 ropes holding onto that one basket. They're tangent to it. This is what's happening. 2 congruent triangles are sitting within it. All righty. This one says that the angle DCB is 70 degrees. So I got it right there, 70 degrees. What is the measure of angle DCA? Ethan.
35.
It is 35. DCA is not even drawn, so you could add that in there if you wanted to. And then 70 is being split into 35 and 35. Bonus question. What's the measure of angle BAC? No, not 75. Ethan? Oh, smaller than that. But you just subtracted wrong, I know. It's going to be 55 degrees. Because this angle here has to be our 90 because it was tangent. And then we did 35. So I did 180 minus 90 minus 35. Got 55. Any questions so far, guys? Okay. All right, theorem 3. If a line is perpendicular to a radius at a point, so if right here we have one single point and that is perpendicular, then that line must be tangent. So this is just the inverse of theorem 1. If it's perpendicular, it has to be tangent. If it's tangent, it has to be perpendicular. So they go hand in hand. If perpendicular, then tangent. All right. I'm actually not even going to go into this one because I think it's a stupid proof. But it's saying if AB is a radius and AB is perpendicular, prove that B is a tangent line. I'll prove that M is a tangent line. Well, it's just the reverse of the definition. If it's tangent, then it's perpendicular. If it's perpendicular, then it's tangent. So we're not going to go into proving that. So you can skip the next slide and go down to slide 12. Determine if ER is tangent at, that's not supposed to be at E, that's supposed to be at R. because that's the point of tangency. Oh, this is very, very badly written. We need another letter. How about a G? And this should be GR. Hey, fix that. ER can't be a tangent line. It's a radius. So we're trying to say that that bottom line is tangent to the circle at R. If it's tangent, what angle is happening? It's a 90. So I'm assuming it's tangent. I'm putting a 90 in there. If that's a 90-degree angle, what should happen with my triangle? Or what should be true about this triangle? Not the P word I'm looking for. Lily. Oh, you're on the right track. If this is 90, then this should work. Pythag should work, because that only works on 90-degree angles. So we can check this. If it doesn't work, that means it wasn't really a 90-degree angle. And I know we did it a while ago, where we actually did this and determined if it was obtuse or acute. We don't need that. We just need to say, yes, it's right, or no, it's not. So 64 plus 64 is 128. That doesn't equal 225. So this is not a right angle. So RG is not tangent. So that's how you do those type of problems. If you're trying to make sure it's tangent, check Pythagorean theorem to make sure it's a 90-degree angle. Okay. Questions there? All right. Last thing. You can have multiple circles being tangent at the same time. Internally tangent means the circles are nested together. And externally tangent is more like the snowman kind of thing. If circles are tangent internally and exterior, then the lines of centers, we're going to change that to a word we understand, then their radiuses pass through the point of tangency. So what they're trying to say in the theorem is AP is one radius, BP is another radius. They become the same line. AP is one radius, BP is another radius. They become the same line. So I want to question you. Oh, where'd my words go? What rule or why does it have to be like this, one on the left, and not the one on the right? Lily, what do you think?
Because it's not like a fully straight line.
But why does it have to be a fully straight line? So this is actually a technique in proofs where you prove that the counter example is not possible. And that thusly proves that the actual example does work. So I've got two counter examples on the right. Let's start with the first one. So this would be the internally tangent. So we've got two circles that meet at tangent point P. Assume that that's one point. If you look real close, it's not. One of the circles had radius A, and one of the circles had radius B. Okay. Well, if they're tangent, this angle here where we have AP is 90 degrees, right? But the B circle was also tangent. So that angle also has to be 90 degrees. So what's going on with this gap? How many degrees in the gap? Has to add up to 180 because that tangent line's a straight line. So that has to be a 0 degree gap. There can't be a gap there. 90 plus 90 equals 180. So that's why these two radiuses are forced to squish together and become the same line, because we've got 90 on the left and 90 on the right. It squeezes them together. So that's why it can't be that way for an internal tangent. Let's take a look at an external tangent. Circle A, point P, point B. AP is tangent, so that's a right angle. And BP is tangent, so that's a right angle. So what is the measure of angle APB? Lily? Should be 180 because it got 90 plus 90, right? So those two 90s adding together is going to force that guy to straighten out and not be bent the way it is. It has to be a straight angle. So that's why it looks like it does over here, and it straightens them out. So that's why that theorem works. And it always will. So internally tangent and externally tangent circles, their centers and their tangent points will all be along the same line. They won't be bent. All right, guys, I am done for today. Any questions on this stuff? Michael at home, any questions on this stuff?